Hi students, this is Mr. Epperson, and this lecture is on Bohr energy shells and valence electrons. In this lecture, you'll learn what energy shells are. Don't worry, they're not too complicated. In fact, you've learned them already, learned about them. And what is a valence electron? Super important concept, one that we'll go back to many times this year. So I don't know if you've ever, let's start off with the phenomenon here. I don't know if you've ever looked at a CD anymore, but if you've ever examined it, you might notice they have like a little bit of a rainbow pattern to them. And the reason for that is this structure in here called a diffraction grating. And it's true in any type of compact disc or, thing that's saved data information in this format. But that's not really the point of today's lecture, but what I want you to see is when you use a diffraction grating, you can actually spread light out from its source into its component colors. You may have heard this before, but light is not just white. In fact, every color of the spectrum potentially is in white light. And all the other colors, the particular colors, have their own wavelength. It's kind of a lot that we could talk about there with physics, but in particular, white light contains all colors of light, and other forms of light only either contain a few colors or just one color. One thing that you can do, and if you have a CD lying around, like I found this one, it got mailed to me from something I'm subscribed to, and it is possible to put it up to one of these. Actually, any light will do, but if you can find a CFL or a compact fluorescent light, either the tube or this kind, you can really see an amazing pattern that happens from looking at these types of lights. And any other type of light will actually just show you the full range of color, but a CFL will show you these particular wavelengths of light that come out of the fluorescent tube. And the reason is because the fluorescent tube actually is containing a bit of mercury, which you might see here. It contains mercury, and that mercury, when you excite it, actually starts to emit particular wavelengths of light. And in this particular example, though, this isn't mercury, this is hydrogen. But when you ionize gas, it gives off light, but it gives light off in particular wavelengths. We call this the quantized behavior of light. Light existing in particular wavelengths that come from particular elements. Now, this is a big concept. You could spend weeks on it. I just wanted to show it to you because it's one of the only ways that we can show the quantum behavior of matter and of electrons in particular in everyday life. And of course, in order to see it, you need a diffraction grating or something like that, like a prism. This has actually been known for many years that if you split up something like a beam of hydrogen that's been ionized and electrified, you can get these bands. They call them spectral bands. And what's interesting about those bands is that it represents kind of like a fingerprint of every element. The reason for this is pretty complex, but it goes back to one fundamental principle in physics that we use to model this behavior in physics called a Bohr model. A Bohr model basically shows us where electrons are going to be. And electrons, according to Niels Bohr, who's this guy here, he was a contemporary of Ernst Rutherford, and they worked together to come up with a lot of interesting and important aspects of atomic theory and how the atom was constructed. And he understood electrons to occupy a particular energy level in an atom. Just like stadiums have seats, right? If you were to say, get your ticket to go to a particular sporting event or something, you would know where you're going to sit. Now, it's best, of course, to sit up at the front, right? Everyone wants to sit up at the front, but eventually you run out of seats. So you have to move back to the next row and the next row and the next row. This is how Bohr understood electrons to behave as well, that you would first fill the lower levels, and then as you would run out of room, you would go to the next level and the next level. So The Bohr model basically has this understanding that a fixed number of electrons can occupy each energy level. You can't put too many electrons in an energy level and just keep packing them in there. Eventually you run out of seats, if you remember that analogy. However, this is a very important rule that you'll have to know. The largest number of electrons that can be in an outer shell, the last shell, the outside shell, the largest number is 8. We call this the octet rule, but we'll learn a bit more about how the octet rule works with bonding a little later. But the largest number is 8. So 8 is the biggest number in the outer shell. The only exceptions are hydrogen and helium, and we'll get to those in a little bit. So without going into a ton more detail, I think it's best to just show some examples here. Let's start off by showing the Bohr structure of hydrogen. Hydrogen has 1 proton, so that's important because when we're trying to draw electrons, we want to know how many protons there are because the electrons and protons should always match. There are no neutrons in this example, but the neutrons don't really matter so much for our purposes of drawing Bohr diagrams. The important factor to know is that elements are always neutral. And what that means is that every time you're seeing an element on the periodic table and you're supposed to figure out how many electrons it has, you assume it has the same number of electrons as it does protons. So elements are always neutral, so the number of protons equals the number of electrons. So that concept has been a little confusing because sometimes we've dealt with this structure called an ion. That type of structure is not important here, at least right now, because ions basically change the number of electrons. It will tell you if you're going to make a Bohr model or a Lewis diagram or whatever we're going over in future lessons, if it's an ion or not. You always assume, though, if you are given an element, it's neutral. So in this case, we're given an element, it's just hydrogen, and it's neutral, so it's got 1 electron. Let's go ahead and draw where that electron goes. There we go. That's the Bohr structure of hydrogen. 1 energy level with 1 electron on it. Okay, let's try helium. Helium has 2 protons, incidentally 2 neutrons, and because it has 2 protons, it's also going to have a matching 2 electrons. So for helium, I'm going to put those 2 electrons on that lower energy level. Now you remember I said that bottom energy level has a max of 2. So this energy level is filled, but we actually have no more electrons to place. So we'll go ahead and call it done. Now we're going up to another row. If you remember how the periodic table is structured, there's helium and hydrogen in row 1, or what we call period 1. You go down to row 2, and we start with lithium. Maybe you now see why lithium is going to be in the second row. If not, hopefully you'll see in just a second. Protons for lithium are 3. Those are positive, and electrons are 3. Those are negative. So if I was to diagram the electrons, I'm going to put 2 here. But now I have to stop because I've run out of seats. I've run out of room to put those electrons. So where are they going to go? Well, I make a new energy level. And now it's represented by that line. I now have a place to put my 3rd electron. And I'm done. Let's try it with another element here. It's fluorine, and fluorine has an atomic number of 9. A little bit more here, but we don't have to worry about it. The number of electrons, pardon me, there is 9. So I'm going to put the lower 2 down first. Now I'm going to move up to the next level, and I'll keep counting. 3, 4, 5, 6, 7, 8, 9. Okay, so in this case, I've put all 9 down, and I've filled up the inner energy level, and I've placed them on the second energy level. And this is a completed Bohr diagram for fluorine. Now that we've got the concept of what a Bohr model looks like and how it's constructed, now I want you to be able to read a Bohr model chart, as you see right above my head here, that shows all of the electrons it placed in their Bohr model diagrams and arrangements, and this concept called the valence electron, okay? The valence electrons are shown here in red. And what a valence electron is, valence electrons are the outermost shell, the electrons in the outermost shell. And we call the outermost shell the place where those valence electrons are. Okay, so that outermost shell is the place where the valence electrons reside, and that's why they're in red here. The non-valence electrons are black. These electrons, the red ones, are the ones involved in bonding with other elements and bonds with other elements and make compounds and molecules. So if you're talking about the molecule water, you would have to understand how the valence electrons interact in order to make bonds between hydrogen and oxygen to make H2O. Here's the interesting thing that you might start noticing patterns on. With the different numbers of valence electrons, we see a pattern forming with the group number. You might have already seen it. The outer electron here is shown in red, and there's one of them. For lithium, right below it, we have another electron by itself that's marked red, and that's the only one in the outer shell. So there's still just one in there. We go up another ring and we get to sodium, Na, but we still only have one electron in the outer shell. So everything in this first group has just one valence electron. If we go to the next group, this element here, beryllium, has 2 electrons in its outer shell. And the one right below it, magnesium, has 2 in its outer shell. So the group number actually tells you how many valence electrons it has. And we can keep going with this trend. You might notice there's a little bit of discrepancy here. The reason for this, again, is that helium can only hold 2 electrons in its outer shell. And so even though all of these hold 8 electrons in their outer shell, helium actually still belongs here because it has the same chemistry as those other elements beneath it. So the chemistry actually supersedes its bonding arrangement, or at least the electrons in the outer shell. It's more important to put it here than here, where it would actually have the same number as the group. So that's how to determine the number of valence electrons. Now, if you had an entire periodic table, like you should have, at least digitally or a printed version somehow, I can keep my head down here because we actually don't care about these actinide lanthanide groups down here. That they do have valence electrons and they're important, but we're not going to study them, at least right now. All we really want to study are these groups and these groups right here. And the reason for that is because this center area, called the transition metals, it doesn't really follow a very predictable trend of calculating the number of valence electrons. There can be a varied amount of valence electrons for something like iron. Iron can sometimes have 2 valence electrons, or it can sometimes actually have 3 valence electrons. And the way that we would know is that in a particular chemical reaction, we would have to tell you which number of valence electrons are being used in that reaction. So don't worry about that right now, but just know that everything in this middle section, kind of that little like valley here, that is sort of off limits with the rule of calculating the number of valence electrons. However, everything on the top area is very easy to calculate. And we do this by looking at the group number, as said previously. The group number is written right up there at the top. Groups are at the top and periods are at the side, right? Period. They go down this way. 1, 2, 3 periods. But the groups go from left to right, and they're columns, right? The first group, we said all of those have 1 valence electron, right? VE for valence electron here. Number 2, group 2 has 2 valence electrons. Now, you notice that there's actually some other names here. Group 1, Group 1A or IA, and Group just 1, letter 1, or numerical 1A. Sometimes we use Roman numerals and sometimes we use numbers, but regardless, you'll notice that it goes 1, 2, 3, but it goes 2A, 3b. So we still call this group group 3 and 3 here, but it's called 3b. These are the B's down here, all the way down here. And everything at the top, not in the valley, we call those the A groups. So 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. And the reason they do that is to simplify how many valence electrons it has, because this is a tool meant to be used by students and chemists alike. How many valence electrons in group 3A? 3, right? It's still the same, 3 valence electrons. So it's nice to know that the A's are there to help you know how many valence electrons there are. Okay, so the trend goes like that all the way across. And like we've said, the only exception to the rule is helium. Helium is an exception because it actually only has 2 valence electrons. That's the only exception. Everything else works beautifully. Okay, so now we're going to do a little bit of quizzing. So can you find where the number of valence electrons that would be in an element like sodium? How many valence electrons in sodium? Well, it's in group 1, so it has 1 valence electron. It's pretty easy. Okay, how many elements would be in an element like oxygen? Well, it's in group 6, so it's got 6 valence electrons. How many elements might be in an element like francium? Well, it's still in group 1, so 1 valence electron. How many elements or valence electrons might be in an element like silver? Well, because it's in that middle area, we actually don't know until somebody tells us. So we won't actually know the number of valence electrons until we get more information. And lastly, how many valence electrons in helium? 2, right? 2 valence electrons, even though all of these in this group are actually going to have, do you know? 8, because they're in group 8 or 18. So helium is the only one that contains 2. Okay, well, that's calculating the number of valence electrons and understanding what they do, and I hope that was helpful.